what is the value of this integral? It seems simple, right? I mean, you just have this integral. We just need to compute it. So let's do that. But I will do it without the integration bounds first. So what happens then? I personally do not like this 1 over x. So I'll choose this u to be equal to 1 over x. And this is an initial idea. We don't like inside functions, so compositions of functions. And the reason I'm moving forward with this is because we do have the derivative of the 1 over x in this expression, which is minus 1 over x squared. If I take the derivative back to u, it's minus 1 over x squared. Which means I can, of course, so I can write this as minus x squared. Put this as follows. Now minus x squared I could also write as minus 1 over u squared. I think that's completely fine just by the definition that we have. So that looks good. I will use the substitution now. So this will give me 1 over x cubed is going to be u cubed, the definition. And then I have e to the, 1 over x is now u. And then instead of dx, I'll write minus 1 over u squared times u. So some things cancel out. Let me get negative u times e to the u du. Then the next question is, how do you integrate this? Well, these are two functions which are not of the same type. This is a polynomial and this is a, what's it called? It's not really a polynomial. I mean, it is an infinite polynomial, but that is something that perhaps I don't want to talk about. It is an exponential function. So that is what I mean. So it is a good idea if we proceed with integration by parts. I will take this to be my u, and this will be my dv. And so I'm looking at the negation of the integration by parts of this. So this will give me uv minus the integral of v times du, which is u times e to the u, because the antiderivative of e to the u is itself, minus the integral, well, the antiderivative of e to the u again is e to the u, and the derivative of this thing is 1 du. And again, the antiderivative of this is 1. So that gives us in the end minus of u e to the u minus e to the u. Perhaps I need to put the plus c, of course, because this is an indefinite integral so far. I'll group e to the u and I'll switch the sign. So this will give me 1 minus u plus c. Now let me write this in terms of x. I think that would be a good idea. So u was 1 over x. e to the 1 over x times 1 minus 1 over x plus c. That looks good, honestly. It looks like we've done some work, and you know, we should be done now. So all we need to do is to plug in the limits, right? The integration limits. But the problem is it's not that easy. Because if you look at it from the beginning, it is very problematic. Let me take this as it is, perhaps without the integral part. And let's look at the domain on which we would like to integrate. You know about the Riemann criterion for integrability. We know that continuous functions are integrable. Within this course, I think we would like our functions to be continuous, or at least in a sense continuous on some finite union of intervals. I think I'll stop. I think I'm making this complicated. So here's what I'm aiming at, really. I mean, if we plug in -1, it's fine, right? You just get e to the 1 over -1 divided by -1. But the problem really, and the big problem really, is when you plug in 0. So e to the 1 over 0 divided by 0. Like, as if one over 0 was not enough. You have two 1 over 0s. And one in the exponential. And you don't know how this will unfold. So this is, I won't say bad. I won't cross it out like this. What I'm going to do is I'm going to put an exclamation mark. Can we make sense out of it? And this is the answer. This is well, it's not the answer for sure. It's the question that I would like to answer for the remainder of this tutorial. So I'll place this as it is, and I'll keep it as a reminder for us. Big box like this. Reminder. Okay, so we have the antiderivative. We could, in principle, write the following: -1, 0, e to the 1 over x, or x cubed dx is equal to this thing, now evaluated at -1 one time, and then at 0 at the other time. But as you can see here, we still have issues with plugging in 0. I cannot really plug in 0 here. I can definitely not plug in 0 there. And so what I would personally recommend is that we take the limit. This is what's called an improper integral. I take the limit as t goes to 0 minus. Why is it a 0 minus? Well, because we're integrating from -1 to 0, but we're going from the negative side. It's this integral. We don't need the 0 positive value. We don't need the function to be, we don't need to know what the function does afterwards. We just need to know what the function does from -1 all the way to 0. So that's why we take the 0 minus, which is basically values that are infinitesimally smaller than 0, which are naturally negative. That's where the minus sign comes from. Nevertheless, so we make this technical remark. Instead of 0 here, I put t, and I continue normally with my problem. That is what I'm going to do right now. Perhaps for the remainder of the solution, I should use a different color. I think red is nice. But what do you think? I think red is nice. I personally like it. So we get to plug in e to the 1 over t first. Times 1 minus 1 over t. And then we take away the value when we plug in minus 1. So we get 1 over minus 1. Maybe I'll write this as minus 1. Then 1 minus 1 over minus 1. That is equal to 2. The last time I checked. I think it would be a good idea if I distribute this. That would give me e to the 1 over t minus 1 over t times the same expression minus e to the minus 1 times 2. That is now the limit that we're looking at. And I think it would be a good idea if we just give me a moment. I want to double check this. Yes, I was confused for a second about the value of this limit, but I'm no longer confused. So I think I'll write this as a limit, as I should write it. There's of course the natural question of how does this evaluate in the end? Now I would like you to notice that if I plug in 0 minus into e to the 1 over t, so I have e to the 1 over 0 minus, this will give me minus infinity. Precisely, it will give me minus infinity. Now, put this in quotations, because I don't want anyone to take a screenshot of this and then show it to my fellow mathematicians, and then they have to call me out using that. So this is more of a disclaimer. Nevertheless, e to the minus infinity is a very small number. It's actually equal to 0. This is something we can see by the graph of the exponential function, which looks like here, I think it's 1, and it decays, so it's an exponential function. For negative values, it decays very slowly, and for positive values, it grows very, very quickly. So that is really the key to solving this problem. The limit of this sum of terms is the sum of each term. Therefore, I could write 0 for this. And here, I could write 0 as well. And you might be wondering why. And there, I would write e to the minus 1 times 2. Why does this go to 0? I think it is a better idea if I write it like this, then it becomes more obvious. Do you know now why we wrote 0 for this limit? Well, the answer is, I hope it is simple. It is because the exponential function, it grows faster than any polynomial, and it decays faster than any polynomial. So it's faster in both directions. It decays very fastly. Did I say very slowly a bit earlier? I hope I did not say that. It decays very quickly and it grows very quickly, actually exponentially fast. So exponential is something we use to emphasize rapid growth or decay, and this is really the case here. E to the 1 over t grows and decays in this case quicker than this polynomial term. So this polynomial term does go to 0, and we get something that looks like 1 over 0, but this is faster. And if we go to 1 over 0 and it's from the negative side, then we get a very small number. And if we get a very small number, then eventually this number goes to 0. And therefore, by this argument, that should be the answer. Maybe a naive argument for that, for why it works, is that if you look at the Taylor series of this thing, you have infinitely many polynomials. And in fact, you can exactly describe this e to the 1 over t in terms of polynomials. And if you have a polynomial of basically infinite degree, then it will definitely be faster than this linear term. This is a third argument for you. I'm giving 3 arguments now. I hope you can at least grasp one of them. But in principle, that's all you need to do for this exercise.